Yes, students, I am really happy to see you all of you here. Here is a one of the discrete problem. It coming in the predicate theory, where we have to using the inference theory we have to prove this. The thing is that lions are dangerous animals. So first one statement. There are lions. Another proposition. Therefore they are dangerous animals. Okay, so this is one statement, this is another statement. We have to prove that therefore they are dangerous animals. Lions are dangerous animals. There are lions, therefore they are dangerous animals. That's what we have to prove. Okay, so, okay, I will minimize the screen so that you can understand well. Okay, now come to the screen. Yes, now if it's no, it is not. I will reduce still so that you can see the full view of. Yes, now it's okay. Now it's okay, I think so. Now look at that. Look at that. So first we have to transform these sentences into a notations, discrete notations we have to change. After that only we can apply the rules there. Okay, so I am taking L of x as x is a lion and D of x is dangerous. L of x is a lion, D of x is a dangerous. If I assumed like this, like this predicates, what I am getting from this is that lions are dangerous animals. So all x where lions are dangerous animals. For all x, for all lions, they are dangerous animals. Lions are dangerous animals implies all lions are dangerous animals. So for all x, L of x, lions are dangerous animals. Second one is there are lions, so there exists some x which are lions, L of x. There exists some x where that x's are lions. That's what the second notation given there. Therefore they are dangerous animals, which implies there exists x, they are dangerous animals. That's what we have to prove here. Okay, so this is one predicate statement. This is another predicate quantifier statement, and last one is also a quantifier predicate statement. With these three statements we have to prove this particular logical ideas or logical conclusion, logical argument we have to prove. This is a method of proving the logical argument. Now how we have to prove this? These are denoting where we are introducing the premise. Okay, that's what this first column. Second column, step number 1, 2, 3, 4, like that. Third column gives you the proper procedure of the next coming. I mean the proper way of proving the next step. That's what this one. And last one is about the reason how that comes. Okay, how that comes. So reasons. This is where we are introducing the premise. Second one is the number of steps. First step, second step, third step, fourth step, fifth step, sixth step. This is a derivation. From here we are deriving the final result. And last one is how that comes, the reason how this is possible, like that. Okay, now I am taking this first premise. First premise, I'm taking that for all x, L of x implies D of x. For all x lions, the lions are dangerous animals. I am taking that. So P is given. Now I can use any logical ideas or logical equivalence idea inside the derivation. So I am bringing the second step, okay, second step, and what is this is at the first step premise is used. That's what this one. The second step is that this is for all x L of x equals d of x. There is a rule which says that if for all x that is true, then for some y, for some y belongs to this particular for all x, this is true. Am I correct? For all x this is true, therefore the particular y that is true. Okay, so instead of x you put y, you will have this L of y implies d of y. For particular y, if the line, then definitely it is dangerous. Am I correct? So what I am using here, the first step I am using, and then the rule, universal specification rule I am using here. This is a universal rule specified for some particular element. So I am getting this. Now next third step is that I am bringing this second predicate quantifier statements into this derivation here. The third step I am bringing them. Okay, so in which step I have brought this premise, I am bringing the third step. So I have written third step. I am bringing this particular premise here. There exists some line x. There exists some x which are lines. Now come here, I am coming to the fourth step. How I am coming to the fourth step? Where the premise used at the first step and the third step are used here in the fourth step. Okay. Now from this I am getting L of y. From there exists x, L of x implies there exists some x. For that x, the line exists. There exists some lines. That's the meaning of this. So there is another rule. If this is a existential quantifier, we can specify some elements to this. That's called existential specification. Existential specification. This is for existential quantifier. This is true. Take for some element y, then that must be a lion. Am I correct? So that's what L of y. For some y, L of y. If there exists some x, L of x. Definitely for some y there exists a lion. So for some y it is lion. Okay. So from the tautology, I am coming to the fifth step. The fifth step, you look at that. The fifth step, this comes. How this comes? I am using the premise used at first step and third step, and then I am using the tautology in the second step. If L of y implies d of y, then d of y. L of y implies d of y, then d of y. That is called tautology we are using there. So if L of y equals d of y, d of y exists. D of y exists. Okay, right. This is step number 5. Now how this step number 6 comes? It comes from existential generalization. This is a particular y. It is dangerous. The existential generalization, this is why I am generalizing to the domain x. So in that case what I will say is that there exists some x for which x those are dangerous. There exists some x for that they are dangerous animals. Okay. There exists some x for that d of x is dangerous. I am using fifth step and the existential generalization property. If this property is satisfied for a single element y, then it is satisfied for some x, some elements in the domain satisfy this condition. So therefore there exists x such that d of x is true. So what I am proving here, I have taken this, at last I proved this. Okay, so this is a way we can prove the trueness of a argument by using inference theory. Okay, right. So in the other class I will take another problem to prove that. So thank you.